In the last screencast, we introduced some new properties of exponents, and we also introduced the idea of a root. In this screencast, we discuss the last two properties of exponents. These two properties will involve roots as well. To motivate these properties, we're going to start off by considering the following example. Example 9.10. Suppose the exponential function p of t equaling 50 times 8 raised to the t over 3 gives the projected size of a population t years from now. So notice that the equation that we're given follows the general template. Y equals b times r raised to the x over delta x. So you can see that the 50 is playing the role of the b, the 8 is playing the role of the r, and the 3 is playing the role of the delta x. Let's go ahead and look at part A. By what factor does the population grow on 3-year intervals? Well, we can see from looking at the equation that 3 is playing the role of delta x. That means we're talking about 3-year time periods, and on 3-year time periods the population is growing by a factor of 8. So the r is 8. That's the factor on 3-year periods. Now let's look at B. Explain why 8 raised to the 1/3 power is the 1-year growth factor. So again, I want to reiterate, 8 is a 3-year factor. In other words, every 3 years this population grows by a factor of 8. In part B, we're talking about a 1-year growth factor. In other words, we want to know over a period of 1 year, by what factor does this population grow? It's not the same thing as 8. Well, let's see if we can figure this out. Let's make a table. And in this table, we'll have time and population size. At time 0, how big is this population? If we substitute 0 in for t in our equation, notice we have 50 times 8 raised to the 0 power, because 0 divided by 3 is 0. 8 raised to the 0 power is 1. So this would become 50 times 1, which is 50. So the initial population size is 50. You can also tell that the initial population size is 50 because if you recall, B represents the initial amount, and in this case that would be the initial population. Now let's figure out what the population value was 1 year later. We can do this by substituting 1 in for t in our function. And if we substitute 1 in for t, we arrive at 50 times 8 raised to the 1/3 power. So we've got our population after 1 year and our population at the start of the year. If we want to know what the 1-year factor is, we take the later amount and divide by the earlier amount. So in this case, the 1-year factor, r, would be found by taking the 50 times 8 to the 1/3 power and dividing that by the earlier amount, namely the 50. You can see that there's a common factor of 50 in the numerator and denominator, which are eligible for canceling, and we're left with 8 to the 1/3 power. So in other words, on every 1 year period, this population grows by a factor of 8 raised to the 1/3 power. That may seem a bit strange to you. This might be the very first time you've ever seen a number that's raised to a fraction. You often don't see fractions in your exponent. So you are perfectly free to question what this means and what is it in general. We'll talk about that. Okay, let's look at part C. According to the exponent property, this is one of the properties we saw in our last screencast. What should this equal? What should it equal? Well, if I take 8 to the 1/3 power and I raise it to the 3rd power, if I apply my property, I should really just take 8 and raise it to the 1/3 times 3. But 1/3 times 3 is equal to 1, so this is really 8 to the 1, or 8. So 8 to the 1/3 power, if you cube it, you get 8. So this is all very strange. Again, we don't even know what this quantity is, but we do know that if we cube it, we get 8. Now let's go ahead and look at part D. Explain why it should follow that 8 to the 1/3 power is equal to the cube root of 8. Well, let's think back to what a cube root is. Remember, the cube root of 8 is the number which, if you cubed it, it would equal 8. So this number sitting in here, that's the cube root, and that's the thing that we write this way. So the cubed root of 8 is the quantity which, if you cubed it, would give you 8. But notice from part C, if we cube this quantity, 8 to the 1/3, we also get 8. Well, there's only one quantity which, if you cubed it, would give you 8, and it's the cube root of 8. So if 8 to the 1/3 cubed, if that's also giving you 8, then that must mean 8 to the 1/3 is exactly the same thing as the cubed root of 8. So 8 to the 1/3 power, it must mean the cubed root of 8. So up here, when we saw this 8 to the 1/3 power and we wondered what it is and what it means, this is what it means. Okay, let's generalize this. This example illustrates two important facts. I'm going to take this fact first. If you take a number and you raise it to a fraction, like here, 1 over n, that is defined to be the nth root of the number. So this is a general version of this right here. If you set the r equal to 8 and the n equal to 3, you can see they are exactly the same thing. But this is true in general. A number r raised to the 1 over n power is defined to be the nth root of r. They are one in the same thing. Also, you also have learned that if a quantity grows or decays exponentially by a factor of r over n units of time, then the quantity also grows or decays by a factor of r to the 1 over n over 1 unit of time. Where did that come from? Well, in our last example, the population grew by a factor of 8, that was the r, over units of time equal to 3. And we found that the quantity grew by a factor of 8 to the 1/3 over 1 unit time periods. This property can be extended as follows. if you have a number and you raise it to a fraction, the result is defined to equal either one of these two quantities. You can either calculate the number r raised to the m and then take the nth root, or you can take the number r, calculate the nth root of it, and then follow that up by raising it to the mth power. So I'll show you in just a moment where this comes from, but it's worth pointing out a couple of things here in this property. The m, the number that's in the numerator of the fraction, represents a power that you're raising a number to, and the n, which is the denominator of the fraction, it always represents a root. So notice when you're looking at this form, n is a root. When you look at it in this form, n is a root. When you're looking at this form, notice that you're raising r to a power of m, and here you're raising the entire quantity to the mth power. So regardless of which form you're looking at, m is always a power and n is always a root. The difference between these two is which of these is done first. This is where order of operations comes in. If you look at this version here, you do what's in the parentheses first. This says take r and calculate its nth root. Then when you're done, raise the quantity to the power m. So in this version, you take the root first and then you raise to the power of m. But in this version, the order is completely reversed. The radical symbol is a grouping symbol, meaning you perform any operation under the radical symbol first. So here you have to raise r to the mth power first before taking the root. So in this case, the power is done first, then the root. So I had promised you that I would show you why these quantities were all equal. So let's go down below and we can work through that calculation. R to the m over n. Well, the fraction m over n can be rewritten in a couple of ways. We can rewrite m over n as m over 1 times 1 over n. And again, if you multiply those two fractions together, you end up with m over n again. This is the same thing as r to the m times 1 over n. And now we can use our exponent property to write this as r to the m raised to the 1 over n. That was an earlier exponent property that we discussed. And now, remember what we said about taking a number and raising it to the 1 over n. If you take a number and you raise it to the 1 over n, what you're doing is you're taking the nth root of that number. So here we're taking the nth root of the number r to the m. So as of right now, I've shown you why these two quantities are equal. Now I'll show you why this quantity is also equal to this quantity. If I go down below, I can rewrite this quantity as r to the 1 over n times m over 1. This is the same as r to the 1 over n times m. Again, using our exponent property, this is r to the 1 over n raised to the m. And again, according to our earlier property, r to the 1 over n is defined to be the nth root of r. So this, in the parentheses, we have the nth root of r raised to the mth power, which is precisely this quantity right here. So I've shown you that r to the m over n is equal to this quantity here. So that is why this property is true. So the last two properties that you need to know regarding exponents are this one and this one. These two properties express the relationship between exponents and roots. Let's try out these properties in the following example, and we're going to assume that all of the variables in this example have positive values. That way we don't have to worry about any roots not existing. Okay, example 9.11. Simplify each of the following expressions using exponent properties. Let's look at part A. 32 raised to the 1/5 power. What does that mean? It means that we are calculating the 5th root of 32. That is what 32 to the 1/5 power is defined to equal. Well, what is the 5th root of 32? Well, we have to ask, what number raised to the 5th power gives us 32? And the answer is 2. Now let's look at part B. We have 1 over 36 to the 1/2. Well, what is 36 to the 1/2? 36 to the 1/2 is defined to be the square root of 36. And the square root of 36, remember, now you're looking for a number which, if you square it, would give you 36. And there are two numbers, 6 and -6. But when we're talking about this symbol, we're only referring to the positive root. So in this case, that would be 6. So that's our final answer. Now let's look at part C. We have 16 raised to the 5/4. Well, remember what we discussed. The 4 here in the denominator represents a root. And the 5 that's in the numerator, that represents a power. To calculate this expression, we are going to have to take the number 16 and raise it to the 5th power and also take the 4th root. We can only do these one at a time. The question is which one we should do first. So think to yourself, would you rather take 16 and raise it to the 5th power and then take the 4th root of that number? Or would you rather calculate the 4th root of 16 and then take the answer and raise that to the 5th power? You have a choice. One of the two options is easier than the other one. If you take 16 and raise it to the 5th power, you're going to get a very large number, and calculating the 4th root of that very large number is not something that would be easy to do without a calculator. On the other hand, if you began by calculating the 4th root of 16, that is a fairly easy calculation to make, and then we can follow that up by raising the answer to the 5th power. So that would be the easier option here. So we're going to take the 4th root of 16 and raise the entire quantity to the 5th power. So the 4th root of 16, what is that? Well, we're looking for a number which, if I raised it to the 4th power, would give 16. In this case, that would be a positive 2 since we're using this radical symbol. So the 4th root of 16 is 2, and 2 is what we are raising to the 5th power, and that will give us a 32. Now let's look at part D. 27 to the negative 2/3. Well, remember what it means to raise a number to a negative power. When we raise a number to a negative power, we get 1 over the same number raised to the positive power. And now we have to calculate this. Just like in our last example, the 3 is a root, and the 2 is a power. So we have to take 27, raise it to the 2nd power, and take a cube root. We have to do both of those things, and again, we can do them in any order we like, but usually one order will be easier. Taking the cube root of 27 first would be a good idea here because the cubed root of 27 is an integer. So we have 1 over, we're going to calculate the cubed root of 27 and square the answer. The cubed root of 27 is the number which, if you cubed it, would give you 27, and that's 3. So the cubed root of 27 is 3. That is what we are squaring, and so our answer is 1/9. Now let's look at part E. This expression involves variables. Once again, we're assuming that the variables are positive values. The numerator is fairly complicated here. We have a product in the parentheses raised to the power of 1/2. Well, you'll recall that we have an earlier exponent property, in particular the one that says if you have a times b to the n, you can rewrite this as a to the n times b to the n. That particular property can be applied in the numerator here. So we could rewrite this as 4 to the 1/2 times x cubed to the 1/2, all of this divided by 8x squared. Now 4 to the 1/2, that's defined to be the square root of 4. And x cubed to the 1/2, using our exponent properties, this is x to the 3 times 1/2. And again, this is divided by 8x squared. The square root of 4 is 2, so I can write a 2 there. And when we multiply 3 by 1/2, we get 3/2. To simplify this fraction, we'll find it useful to separate the numerical part of the fraction, namely the 2/8, from the variable part of the fraction involving the x's. And I'm separating these two into two smaller fractions that we will multiply. Now, 2/8 simplifies to 1/4. To simplify the fraction involving the x's, we can use our earlier exponent property that says if you have a number raised to a power divided by the same number raised to another power, you can calculate the quotient by subtracting the powers. So here, that would be x to the 3/2 minus 2. So we have 1/4 times. Now 3/2, that's the same as 1 1/2. 1½ minus 2 is a negative 1/2. So really this is x to the negative 1/2. This is fully simplified at this point, but as we've mentioned earlier, leaving your answer with negative exponents, and in particular fractional exponents, is not always a good idea. So let's rewrite our answer with no negative exponent, and let's rewrite the fractional exponent as a root. So first of all, let's deal with the negative. An x to the negative 1/2 is defined to be 1 over x to the 1/2. And x to the 1/2 is defined to be the square root of x. So really what we have is 1 over 4 times the square root of x. And this would be the preferred way of leaving our final answer. Okay, let's go ahead and look at example 9.12. This example focuses on roots that do not have simple integer values. Use a calculator to give a decimal approximation for each of the following roots. So we'll do this in a two-step process. Let's look at part A. First of all, let's write the number the 4th root of 9 using exponents. So the 4th root of 9 is by definition 9 raised to the 1/4 power. So now if we move on to B, we can use a calculator to obtain the decimal approximation of the 4th root of 9 by instead calculating 9 to the 1/4 power on our calculator. So what we have is the 4th root of 9 is the same thing as 9 to the 1/4 power. You can also rewrite this as 9 to the 0.25 power. And on your calculator you can type this in with a 9 and a caret and a 0.25, and if you type that in, you arrive at a decimal 1.732, and it continues on. So this would be a way for you to calculate more complicated roots on your calculator. It's worth pointing out that we're trying to find the 4th root of 9. In other words, we're trying to find a number which, if you raised it to the 4th power, would give you 9. There's no simple value for this number. So this is a more complicated root. So this would be an ideal time for you to want to obtain a decimal approximation for the root. So again, to calculate the 4th root of 9, to obtain a decimal approximation, rewrite the root as an exponent in this form. Once you've rewritten it as an exponent, you can put it into your calculator to obtain a decimal representation for the root. Now let's go ahead and look at example 9.13. Use exponent properties to simplify each of the following algebraic expressions that involve roots. Assume all variables have positive values. So in this example, every part is going to involve a root, and your goal is to simplify that root using the exponent properties you've learned. Let's start with part A. So notice we have 5 over the square root of 5, and we want to simplify. Well, 5 in the numerator, that's the same as 5 over 1. The square root of 5 in the denominator, we can rewrite that with exponents. A square root is exactly the same thing as a 1/2 power. So how would we simplify this fraction? If we have 5 to a power divided by 5 to another power, notice we can calculate the answer by taking 5 and raising that to the difference of the powers. 1 minus a half is a half, so this is really 5 to the 1/2 power. And 5 to the 1/2 power is defined to be the square root of 5. So we started off with an expression that involved roots. We simplified it down to another expression that involves roots, but along the way we converted all of the roots to exponents, and then we just simply used our exponent rules to simplify. So that's how many of these parts of this example will work. Okay, now let's look at part B. Here we're calculating the cubed root of x cubed. Well, the cubed root of a number is the same thing as the number raised to the 1/3 power. So instead of taking the cubed root of x cubed, we're going to take x cubed and raise it to the 1/3 power. Now, using our exponent properties, we know that this should be the same as x to the 3 times 1/3. 3 times 1/3 is equal to 1, and this is really just x. So the cubed root of x cubed is the same thing as x. Let's look at part C. Here we're taking the square root of 25y to the 8th. Let's take the square root and rewrite it as a power. So we take 25y to the 8th, and instead of taking the square root, we're going to raise it to the 1/2 power. Now we can use our exponent properties. Inside the parentheses, we have a product. And anytime you have a product raised to a power, you can take each factor and raise it to that power and then multiply. That was one of our earlier exponent properties. Now, 25 to the 1/2 power, that's the same thing as the square root of 25. And we can use an exponent property to rewrite y to the 8th to the 1/2 as y to the 8 times 1/2. Now, the square root of 25 is 5, and y to the 8 times 1/2 is the same thing as y to the 4, and so that would be our simplified answer. Let's look at part D. Here we're taking the square root of a fraction. So let's begin by writing the square root as an exponent. So we have p to the 4th over 16, and instead of taking the square root of this, we're going to raise it to the 1/2 power. Now we have an exponent property we can use. We can take the 1/2 power and distribute it to the numerator and to the denominator. In the numerator, we can use another exponent property to rewrite this as p to the 4 times 1/2, and in the denominator, we have 16 to the 1/2 power. That is defined to be the square root of 16. In the numerator, we have p raised to the 4 times 1/2, but 4 times 1/2 is 2. And in the denominator, we have the square root of 16, which is 4. So that is the simplified form. Now let's go ahead and look at part E. Here we're calculating the 4th root of x to the 5th. We begin by writing the root as an exponent. So we have x to the 5th power. The 4th root of this is the same thing as raising this to the 1/4 power. Using our exponent properties, we see that this is the same thing as x to the 5 times 1/4. And when we multiply 5 by 1/4, we know we arrive at 5/4. 5/4 is the same thing as 1 1/4. And 1 1/4, that's the same thing as 1 plus 1/4 more. Again, using our exponent properties, this is the same thing as x to the 1 times x to the 1/4. And x to the 1 is x to the 1/4 is the 4th root of x. And this would be our simplified answer. So you may be looking at this and thinking, well, that doesn't look much simpler than what we started from. The goal in this exercise was really to reduce the power on x. You can see in the original statement that the power on x was 5, and in particular that power was larger than the root. 5 is larger than 4. What we've done in our work here is we've reduced the size of that power, so that notice now we're not raising x to a large power anymore. We just have x, the 4th root of x, times another x. So we brought down that power.